In this session, we consider the repeated real case. As I explained, when you substitute y equal exponential mx into the second order differential equation, you have a m squares plus bm plus c equals 0. When the b squares minus 4ac equals 0, we have a single root m equal minus b over 2a. We find the single solution of the y sub 1 equal exponential mx. M is expressed minus b over 2a. But we need to find another solutions. I explained the reduction order method to find another solutions. We happen to know a solution y sub 1 over second order differential equations. y2 prime plus p is a function of x times y prime plus q is a function of x times y equals 0. So we consider second solutions expressed as y sub 2 is a function of u times y sub 1. Y sub 1 is one of the solutions of differential equations. So if you consider the constant value times the y sub 1 is a solution, but it is not an independent solution. We'd like to find the independent solutions of y sub 2. So we consider the variable of the u. U is a function of x. And substitute these solutions into the differential equations. So to substitute the differential equations, we need to find the derivative of y sub 2 with respect to x. So first derivative, we apply the derivative or product of the two functions. So y sub 2 prime is u prime times y sub 1 plus u times y sub 1 prime. And second derivatives, one more derivatives of this functions is becomes u2 prime times y sub 1 plus 2 times u prime times y sub 1 prime plus u times y sub 1 2 primes. This is second derivative. So you can substitute these equations into the original differential equation. So this has to be the 0. So you have these equations. The y sub 1 2 prime p y sub 1 prime plus q times y sub 1 is from the assumptions y sub 1 is a solution of the differential equations. This has to be 0. So from this equation, this is gonna be 0. So we have a u2 prime times y sub 1 plus 2 times y sub 1 prime plus p y sub 1 times u prime equals 0. So if you look at this equation, there is no u terms. So we could use the substitution method. W equal u prime into the second order differential equations. Then w prime equal u 2 primes. So w prime times y sub 1 plus 2y sub 1 prime plus py sub 1 times w. So we have a first order differential equations of w. W prime is a dw dx. And the y sub 1 prime is a dy sub 1 over dx. Then we could express this equation into this ones by dividing by the y sub 1 w in the both sides of the equation and multiply the dx in the both sides of the equations. Then dw over w is actually this is d natural log w. And also the dy sub 1 over y sub 1 is a d log y sub 1. And then we can express this way. We can combine these equations using the log law. So this is w and y sub 1 squares. Log w y sub 1 square becomes integral minus p dx. Instead of the natural log, if you take exponential functions, w y sub 1 square equals c sub 1 times exponential integral minus p dx. So w is expressed, and w is a derivative of the u with respect to x. Then by integrating in the both sides of the equation, you have an expression for u. We are happy to find another solution. So we could choose c sub 2 is 0. C sub 1 is fine to find another solution. With only one solution with the y sub 1 equal exponential mx, we can find another solution using the reduction order method. Y sub 2, y sub 1 over exponential minus p dx over y sub 1 squared. In this case, p is expressed b over a. So exponential minus p dx gonna be exponential. This is equals m is expressed minus b over 2a exponential 2mx. This is equal to the exponential 2mx. Then you can substitute. Y sub 1 is exponential mx integral exponential 2mx over exponential 2mx dx. This is cancel out. So solution is expressed x exponential mx. So this is another solution. So x times exponential mx. The general solution is given by y equals c sub 1 exponential mx plus c sub 2 x times exponential mx. This is general solution. Also, I can show you another method to find the general solutions. In the case of the m sub 1 equal m sub 2 equal m, then differential equation is expressed y2 prime minus 2my prime plus m squares. So if you use a differential operator of capital D, the d minus m times d minus my equals 0. Then we multiply the exponential minus mx in the both sides of the equations. As I explained, we could combine these two into the single terms. So we can switch the terms, exponential mx inside of the d. d minus my equals 0. Then again, you could find another exponential minus mx d minus m. Again, we can switch the terms. Then it becomes exponential mx becomes inside of the d. Then capital D twice. So d squared times exponential minus mxy equals 0. Then we could integrate in the both sides of the equation. So this is second derivative. If you integrate of the 0 in the one time, there is a c sub 1. One more integral becomes the c sub 1 x plus c sub 2. So exponential minus mxy equals c sub 1 x plus c sub 2. By multiplying the exponential mx in the both sides, we have a solution of that. Y equals c sub 1 x plus c sub 2 times exponential mx. So this solution exactly same with these functions. I explained the two methods to find general solutions in the case of the repeated real root. In this case, we only consider the repeated real root has the two solutions. But in general, you could write the d minus m to the n y equals 0. Then you multiply the exponential minus mx in the both sides of the equation. And then we repeat the same type of the calculation. Finally, you can find exponential minus mx y equals 0. If you integrate n times in the both sides of the equations, exponential minus mx y becomes c sub 0 plus c sub 1x plus c sub 2x squared plus blah 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 up to the c sub n minus 1 exponential n minus 1. So y is expressed exponential mx c sub 0 plus c sub 1x plus c sub 2x squared plus blah 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 plus c sub n minus 1 x to the n minus 1. Okay, this is the general solution. Okay, this is the end of this session.